if we're given some series here, and we assume it converges, so we'll assume that the series converges, so what that means is we can actually sum this thing up. So since there are infinitely many number of terms, it stands to reason that then the terms must get arbitrarily tiny the further out you go. Because, if there's some substantial number, if you get 1 plus 1 plus 1 plus 1, well, that'll be infinity, because the series goes out forever. So, in order for a series to if a series converges, then the values of the terms must get arbitrarily tiny the further out you go. So this is just a fact. So this means that since the series converges, therefore, we can just write this as a math statement. We have that the limit as n goes to infinity of the terms, they become arbitrarily tiny, so they get closer and closer and closer and closer to 0. So anytime you have a convergent, if you have a series that converges, so if this series converges, this is a series that converges, it implies this condition here. And so we can turn this around, and this gives us what's called the divergence test. So this theorem is just the contrapositive of this statement in red. If you have a convergent series, then the limit of the terms in the series vanishes the further in the series you go. So the contrapositive of that says the following. It says that if the limit as n goes to infinity of an is not 0, then the series obtained by summing over all these terms diverges. And so this is this result here is called the divergence test. So it only tells you, it doesn't tell you anything about convergence. It only gives you negative information. It only tells you whether or not the series diverges. It doesn't tell you anything about convergence. So let's do an example. So let's consider the series summation n goes from 1 to infinity of, say, n over 3n minus 1. So what we can do, so here the nth term in this series is n over 3n minus 1, and so we can compute the limit as n goes to infinity of these terms. That's the limit as n goes to infinity of n over 3n minus 1. And you should see that this gives you 1/3. But how do we do that? We can use properties of limits. We can factor out the n on the bottom. Factor that out. That gives us a 3 minus 1 over n. And then properties of limits are very well behaved. We can cancel that out. So this is the same thing as the limit as n goes to infinity of 1 over 3 minus 1 over n. Of course, as n goes to infinity, 1 over n becomes 0. So this becomes 1/3. Of course, this is not 0. And so, therefore, the series diverges. So this series here has to diverge. Okay, so this is an example of this divergence test. So if you have a series, the first thing you want to do is calculate the limit of the terms, the limit as you go out to infinity. If the limit is not 0, then it will automatically diverge. So then you can just, there's nothing you can do. Let's do another example. Say if we have the, say, n goes from 1 to infinity of e to the 1 over n squared. So now, so does this diverge or converge? So here an, the nth term in this series is e to the 1 over n squared. And so if we calculate the limit, as these terms get further and further and further out, we want them to become really, really tiny, but they vanish as you go out to infinity. But remember, limits are very, very well behaved, so as n goes to infinity, this thing here is going to 0. So this whole limit is actually e to the 0, which is 1, which is still not equal to 0. Hence, this series also diverges. So this series here also diverges. Okay, so one more time, the statement is that if the limit of the terms as you go out to infinity is not 0, if it's not 0, then it necessarily diverges. I just want to give you one more incomplete example. So here's kind of a example. This is to emphasize that the theorem only tells you one direction. It just says if the limit is not 0, then it diverges. So I just want to tell you that this series here, 1 plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, plus 1 over 6, on forever. This is called the harmonic series. Harmonic series. This diverges. Even though, so what does the series look like? This series is the summation, n goes from 1 to infinity of 1 over n. And so if you calculate the limit as n goes to infinity of these terms, you actually get 0. Okay? So the point is that you just have to remember that just because the limit as n goes to infinity of an equals 0, it does not mean the series converges. Okay, so sorry, that's pretty bad handwriting. So in other words, the only information you can conclude using the divergence test is whether or not a series diverges. That's why it's called the divergence test. So in order to use the divergence test, you calculate. The divergence test only answers the question, do we know for certain if it diverges? And so one way to know for certain that it diverges is if the limit as n goes to infinity of the terms is not equal to 0, then we can conclude it automatically diverges. But it could still diverge for other reasons, so you just have to be very careful when using the divergence.